Hello, I'm Francisco Barros, and this presentation is about the displacement monitoring of crossbeams in an airport runway extension using digital image correlation. And we'll start with a quick overview. The runway at Madeira Airport is quite unique, since it has a section suspended above the sea at a height of 60 meters. And normally aircraft land in the southwest and northeast direction, but occasionally they will land from northeast to southwest, and when that happens they come in contact with the runway on the suspended section. And the objective of this project is to evaluate the displacement and strain on the supporting beams when these landings occur. And for such purpose we developed a monitoring system based on digital image correlation, which not only allows the evaluation of these measurements, but also their comparison over time to detect changes in behavior. And our monitoring system consists of a speckle pattern, as is usually used in DIC, on the middle section of a beam with 2 meters by 1. And a camera mounted over a pillar on the adjacent beam, and this is because the displacement exactly over the pillar will be negligible compared to the displacement on the middle of the beam. Two systems were assembled on 2 beams on the touchdown zone where airplanes are most likely to land, so these beams will likely have the highest loads. And this is the system for which we need a high resolution and a high frame rate, because displacements are small and we're looking from a long distance, and the load happens for a very short time. So as I've mentioned, cameras are mounted on the beams directly over pillars. This assembly includes steel housing, which includes the camera inside with a 300mm lens, a controller for the wiper system, and additional hardware related to the camera and the wiper system. Then outside this housing we have the wiper system itself, consisting of the wiper and a water tank with a pump, and the assembly is connected to a power supply, obviously, optical fiber to control the image acquisition and the transfer data, and a water supply to refill the water tank when needed. And all of these components were fastened to the concrete structure with screwed connections. A speckle pattern with reference targets was painted on the beam, and then after all the connections were completed in the camera assembly, the cameras were directed towards the patterns and focused. And in the end, a calibration procedure was done in order to correct perspective. This is because the pattern and the camera have an angle of about 27 degrees between them, because the camera is on the pillar and the pattern is in the middle section of the beam. Now we'll go over the physical infrastructure for data acquisition and treatment. As established before, we have 2 cameras on 2 beams. And then on the firefighters outpost, which is about halfway across the length of the runway, and is essentially the closest closed space to the cameras, we have 2 workstations which will control the image acquisition, which are connected to the cameras using optical fiber. And these workstations are responsible for the image acquisition and some processing. And in the end, there is a server in the control room that's connected to these workstations through a local network, and the data will be transferred to that server, and we will do the rest of the processing and visualization on the server. We have 2 different programs running on the workstations. So one of them runs during daytime, which is not only when we have flights but also when we have sunlight. And this program communicates with the camera and acquires images of the speckle pattern. And these images are continuously compared to a reference taken at the beginning using a rough DIC computation, prioritizing computational performance, because there are 90 images coming in per second and we must process them quickly. And then when it detects a displacement, it saves a sequence of frames from before the event, which by that time are still in memory, and then from after the event. And then during the night time, it goes through every saved event using a more careful DIC algorithm with a sub-pixel resolution on a small area, obtaining its rigid displacement over time. At this point, if it detects that this was not a true event and the displacement came from a camera error, or that the displacement was overestimated by the rough algorithm, it will delete that event, and otherwise it will send it to the server, and it will send the data it processed as well as the image of the most critical point, the point with the highest displacement. And then on the server we have software that takes the images and corrects perspective, and then calculates the displacement and strain fields for the critical image of each event. And then we have a program which we can use to visualize these fields, as well as the rigid displacement over time, and we can also compare these displacements for several events that we can select. And we also have a program that goes through the measurements that are sent over by the workstation every day, and if it detects an event with a high displacement amplitude, it sends an email alert automatically. So now onto the results. We were able to detect displacements on events that we were able to verify were real, and they corresponded not only to landings, as was the original intention, but also to takeoffs and taxi operations. And you can see graphs for all of these types of operations here at the bottom of the slide, where positive displacement is downward deflection, and deflections were around 1 millimeter in order of magnitude, which in the camera corresponded to about 2 pixels. We were also able to compare the results from the IC with vertical accelerometers installed on the same beams, and their numerical double integration will give us values corresponding to displacements. This is an example of an event which we analyzed, but we analyzed several events and the conclusions were always the same. So the shape of this curve is always similar between the DIC and the double integration of the accelerometer, but the magnitudes are mismatching. We suspect this may have to do with some loss of data quality due to the numerical double integration, but we cannot be completely certain. And finally, we have the displacement and strain fields coming from the DIC analysis of the full images. Displacement fields mostly show us values around the rigid displacement without a clear pattern, and strain fields are mostly noisy, and they only show high magnitude values in regions with high correlation errors caused by known issues, such as areas of the pattern with low contrast, or cables from strain gauges passing in front of the pattern. And this indicates that so far for all the events recorded, strain values were simply too small to measure, and a similar conclusion was reached for these strain gauges also installed at the same location. And so in the future, critical events with higher displacement magnitudes might produce some more interesting values for these fields, but as it stands they don't add much information to the already previously presented results. And so to conclude, we can first remark on the successful installation of a computer vision monitoring system for deflection measurement on the runway's beams. And this includes a robust camera assembly at a location with difficult access, the whole infrastructure for communication and control, the software which automatically controls the acquisition and processes and transfers the data, and interactive software which allows us to process and visualize the data. As for the system's operation and performance, we were able to detect events on the runway that are part of the airport's daily operation, and not only landings but also takeoffs and taxi operations. We were able to develop a tool that acquires, processes and stores all the data automatically with minimal human interaction, and we were able to quantify the displacement in the beams under analysis, whereas strain values so far have been too small to be measured. Thank you very much.